Well, hello everyone. It's great to be with you virtually. I'm very grateful to Andrew Hayes and Corey Stephen for inviting me to give this talk as part of a panel on tutorials for digital text and document processing. My name is Robert Turnbull. I'm a Senior Research Data Specialist at the Melbourne Data Analytics Platform at the University of Melbourne. We collaborate with academics from many different disciplines to apply data science techniques to their research questions. My own research focuses on medieval translations of the New Testament from Greek into Arabic. My presentation is called Practical Image Processing for Manuscripts on the Command Line. Over the years, I've had to learn a variety of techniques for processing manuscript images using open source software, and I hope that some of the tips and tricks that I share will be useful for you as well. You don't need to work specifically with manuscript images to benefit from these tools. Many of the techniques I discuss will also be useful in working with digital images of printed documents and other archival materials. Facsimiles of historical manuscripts are today available at an unprecedented scale. From almost anywhere in the world, scholars can view and often download ancient and medieval manuscripts from collections such as the Vatican, the Bibliothèque Nationale de France, St. Catherine Sinai, and the University of Cambridge. Once these images have been obtained, however, the challenge becomes how to work with them efficiently, reproducibly, and at scale. Fortunately, there's a large ecosystem of open source tools that can assist with processing manuscript images. Many of these tools follow the Unix philosophy of do one thing and do it well. Individually, these programs are small and specialized, but they can be combined into powerful and flexible workflows. To illustrate these tools, we'll be using a case study of Jerusalem Agios Stavros 26, which is an 11th century Greek-Arabic lectionary written on parchment, with the Gregory Allen number of L1023. In 1949, the Library of Congress sent an expedition led by Kenneth Clark to Jerusalem and St. Catherine's Monastery at Sinai to microfilm manuscripts. These microfilms have been digitized and placed in the public domain and are available through the Library of Congress website. The first step is to download the images. We can download this image using wget. It's available on Linux, Mac, and Windows. The basic usage of wget takes the form as seen on the screen, where you provide the URL you want to download and the path where you wish to save the output. The Library of Congress provides downloadable full-resolution images for each two-page spread. The images are served using the International Image Interoperability Framework, or IIIF. The URLs follow a predictable pattern with a base URL like this, and then a suffix which includes a zero-padded 4-digit page number highlighted in yellow. To download these images, create a new directory called Stavros26-LOC with a make-dir command. Single images may be downloaded like this, where we first create a variable with the URL and then create the output path to the new directory and then download with wget. To download all the 377 images for this manuscript, we use a loop. The seek command generates the list of page numbers from 1 to 337, and the -w option pads the numbers with leading zeros. For each page number, we construct the IIIF URL dynamically using the base URL together with the current page number. We also create a corresponding output file name for the downloaded image. The wget command then downloads the image and saves it to disk with that file name. Finally, the sleep2 command pauses for 2 seconds between downloads. That's important because it avoids sending hundreds of requests to the IIIF server at once, and it's more polite to the server and reduces the risk of being rate limited or blocked. Now that all the images have been downloaded, each microfilm image contains two manuscript pages microfilmed together in a single frame. To make the images easier to read and process, we first want to split each image into separate sides. Here we can use the Python tool called MSS Tools, developed by me and Peter Montoro, to split these images automatically. It's best to install this program inside of Python virtual environment so it doesn't affect the system-wide Python installation. As you can see how to do that here, where we install MSS Tools using pip. MSS Tools includes a command called split images, which separates left and right pages while preserving a small overlap around the gutter. This overlap helps ensure that the text near the binding isn't lost during the split. The simplest usage is like this, where we run split images, give the prefix of for the files that we want to create, and then give it the images. We want to add a few custom options provided by the tool. For example, the images are split with a 10% overlap by default. We want to reduce that to 6% here with the -- overlap 6 option. Since the first 3 pages of this collection are title cards rather than manuscript images, we can skip them with the -- skip option. We'll also adjust the margins to better center the fold in the image. This manuscript is ordered from left to right, which is the default behavior in MSS tools. Manuscripts ordered from right to left can instead use the -- RTL flag. If we want output files to include the correct recto and verso folio numbers, we can specify the first numbered recto page with the option -- recto, and then the file name and the folio number. As is sometimes the case, the folio numbering in this manuscript isn't entirely consistent. So additional folio labels can be supplied to correct the numbering at particular points in the sequence. There's also one image which is a duplicate, and we're going to ignore that with the -- option, ignore option. So once we run this command, the images are now split into individual pages with the appropriate folio numbers included in the file names. Some of the images are not perfectly aligned, meaning that the lines of text are slightly skewed at an angle, as you see here. Now we'll use the deskew utility developed by Stefan Brunner. This software uses a canny edge detector on the image and then applies a Huff line transform to identify the dominant line orientations and estimate the page skew. Deskew can be installed from the Python package index using pip like this. First, deskew can be used to detect the skew angle. In the case of 297 verso, we can detect the skew angle using the command like this. And deskew reports that the image is skewed approximately 5 degrees anti-clockwise. The image can then be corrected automatically. First, we create a new directory called Stavros26 deskewed and write the corrected image to it. The same operation can be applied to the entire collection using a loop like this. This creates a list of all the images in the split directory, then processes each using deskew and stores the corrected output in the Stavros26 deskew directory. We can automatically crop much of the black background surrounding these manuscript images. To do this, we can use ImageMagick. On Mac OS, ImageMagick is installed using Homebrew, and on Linux systems, it can be installed using the system package manager, for example, apt install ImageMagick. To determine how much of the image should be cropped, we first identify a bounding box around each manuscript page. The bounding box is a rectangle that encloses the region we wish to keep. We begin by storing the path to the input image in a variable. We then ask ImageMagick to detect the bounding box automatically. This command here examines the colors around the edges of the image and treats those pixels as background. The -fuzz 30% option allows pixels that are similar to the background color to be also considered as part of the background. ImageMagick then determines the smallest rectangle that excludes all this connected background region. The output is stored in a variable called bounding box, which is a string which looks like this. This format represents the width, height, starting x coordinate and starting y coordinate respectively. These values can be separated into individual variables using the read command. Here, IFS stands for internal field separator. It tells the read command to split wherever it encounters either an X or a plus character. Now we can use these values to draw a bounding box, as seen here, using this command here. The resulting bounding box removes some of the background. However, there are small artifacts from microfilm near the top and bottom edges, which prevent the crop from fitting tightly around the manuscript page, as seen in the image. To ignore these small artifacts, we can first transform the image before detecting the bounding box. This can be done using the command you see on the screen. The threshold option converts the image into black and white pixels, And the open disk morphology then removes small bright or dark artifacts that are smaller than the disk size. The result is seen here on the screen. This allows the bounding box calculation to focus on the page itself rather than the isolated noise around the borders. We can again draw the resulting bounding box onto the original image. This produces a bounding box that aligns much more closely to the edges of the manuscript page. Finally, we can enlarge the bounding box slightly with a margin of 50 pixels on each side and crop all the images automatically in a loop and store the resulting images in a directory called Stavros26 cropped. And that's what you see here. Now, sometimes the contrast of a microfilm image is not ideal for reading the text clearly. In these cases, the contrast can be enhanced automatically using ImageMagick. One simple approach is to normalize each image. In ImageMagick, normalization stretches the range of intensity values so that darker pixels become darker and lighter pixels become lighter, increasing the overall contrast of the image. For example, you can see the command on the screen for one particular page, 194 recto. This increases the dynamic range of the image by spreading the pixel intensities across a wider range of brightness values, as you can see in the histogram images. And the histogram plots show the distribution of pixel brightness values in the image, from black on the left to white on the right. To normalize the entire collection, we can use a loop, like this. This finds all the images in the directory with the crops and processes each using ImageMagick's normalize command, and then stores the normalized results in a directory called Stavros26 normalized. Now that the images have been processed, they can be combined into a single PDF document for easy viewing, sharing, and distribution. Some tools which you can use to combine images into a PDF re-encode the images, which is slow and can increase the file size. So instead, MSS tools can be used to combine the images into a PDF without re-encoding the JPEG files. The resulting PDF also includes bookmarks so that folio references appear in the table of contents in the PDF viewer, as you see here. So this command takes all the images from the normalized directory and saves them into a PDF called stavros26.pdf. The strip pattern option ignores the prefix in the file name to just bookmark the page and the folio numbers for the table of contents. Now, you might already have a manuscript in PDF format and you wish to extract all the images as extract all the pages as separate images. For this, you can use an application called PDF Images, which is part of the Poplar Utils library. On Mac OS, this can be installed with Homebrew like this. And on Linux, it can be installed with a package manager such as apt-install Poplar Utils. To extract images from a PDF, run a command like this. This creates a new directory and then takes the Stavros26 document and extracts all the images to the prefix provided at the end without re-encoding the images. This means that all the images are identical to the ones we used to create this PDF document. Well, this paper has introduced the practical workflow for processing manuscript facsimiles using command line tools. Starting from publicly available digitized microfilms, we downloaded the manuscript images, split page spreads, corrected skewed pages, automatically cropped borders, enhanced the image contrast, combined the processed images into a PDF document, and then finally extracted the images back from the PDF. You can see the code for each of these steps online. Now, not every manuscript collection requires all these steps, and different collections may require different parameters or workflows. Nevertheless, the examples presented here demonstrate how relatively small command line utilities can be combined into flexible pre-processing pipelines. One of the major advantages of command line workflows is reproducibility. Once a workflow has been developed, it can be rerun consistently across hundreds or thousands of images, making large-scale manuscript processing substantially more efficient. These workflows are highly adaptable and can be easily modified for different collections, image qualities, and research goals. The examples in this paper only scratch the surface of what's possible with command line image processing. Powerful tools such as ImageMagick provide many additional operations for image enhancement, such as filtering, thresholding, resizing, color correction, and format conversion. As digitised manuscript collections grow in scale and availability, command line workflows can provide an efficient and transparent approach for managing and processing manuscript images. Well, thanks very much.